Hello and welcome. My name is Ian Hernandez, and today I'll be presenting our research on the microwave-assisted delignification of agave angustifolia bagasse for enhanced cellulose yield. We are part of the Research Center for Applied Science and Advanced Technology, Legaria Unit, located in Mexico City. This project was originally driven by two main concerns, the first one being the environmental impact of agro-industrial waste. In our case, the waste was generated from agave bagasse, from the two biggest industries right now in Mexico, those being tequila and mezcal production. And secondly, our second concern being the cost and inefficiency associated with traditional cellulose extraction methods. This is because the main component of the bagasse is cellulose, and because it also has the most applications out of the components that make up the composition of the bagasse. With that in mind, our goal was to develop a faster, greener, and more efficient approach using microwave-assisted extraction. We began by treating the agave bagasse with sodium hydroxide in a first step, which we coined as alkaline extraction, by adding the agave bagasse fibers into a 5% sodium hydroxide solution and applying 1000 watts of microwave energy for 5 minutes. This treatment helps break down lignin and hemicellulose, allowing them to dissolve into the solution and to be easily removed. What's left are the delignified fibers, primarily composed of cellulose, though still with some residual impurities on its surface. And to remove those, we had to move on to the bleaching step, which was using a 5% hydrogen peroxide solution, again treated by or aided by the microwave energy to enhance the process and reduce the chemical usage, which resulted in us obtaining quote-unquote purified cellulose. And to evaluate the quality of the extracted cellulose and to make sure that what we obtained was cellulose, we used several characterization techniques. The first one being Fourier transform infrared spectroscopy to identify key functional groups and confirm chemical structure to avoid mainly depolymerization, and to make sure that each step really does what it's meant to do. For example, in the alkaline extraction, we expect for most of the lignin and most of the hemicellulose to leave, while in the bleaching step, we mainly expect for cellulose to be present and nothing else. Next, we employed X-ray diffraction analysis to determine the crystallinity of the cellulose, which also can be related to its purity. And finally, scanning electron microscopy to observe the surface morphology and fiber structure. Moving on to the results showed clear improvements. Lignin removal increased from 65.8% to 87.6%, meaning an improvement by 33%. Cellulose yield rose from 53.4% to 79.2%, meant an improvement of 48%. Reaction time dropped by 70%, though this is a bit tricky because there are so many conventional methods, and we opted for kinda just a general time for the conventional method. And finally, for the reagents used, we used about 50% less reagents than those used in conventional methods. In terms of energy and water consumption, we also witnessed that the resources needed are nearly half of what conventional methods use, which considerably adds to the process efficiency. Moving on to the characterization methods, here we have the spectra of three samples. The first one being a reference sample of cellulose from Sigma Aldrich, then a alkali treated sample from our method, and finally a bleach sample from our method. As we can see, as we follow the steps and as we reach the bleaching step, we can see that the cellulose obtained in that step, it closely resembles the cellulose from our reference, and we can see it reflected in the spectra in the peaks related to 2900 and 3300, which are associated with cellulose type 1. And also the glycosidic bond, which I mentioned, would also be important to ensure that there is no depolymerization. Though, before moving on, something else to keep note of, that in the extraction step there is still presence of lignin and hemicellulose, noted by the peaks on the table in your screen. And as we can see, the process really is efficient at removing lignin and hemicellulose, leaving us just pure cellulose. Next we move on to the X-ray diffraction analysis, in which we calculated its crystallinity index, which resulted to be 84.41%, relatively high when compared to other studies. Then again, adding to our method being better than conventional methods, and showing us peaks that indicate a well-ordered crystalline region, and also some peaks that are related to the amorphous and less organized crystal domains. But still, nonetheless, having a CI of 84% shows great promise and tells us that our purity is relatively high and that our cellulose could be used for biomedical applications or reinforcement of materials, aside from paper making or cardboard making. Finally, moving on to the results of the characterization by microscopy, we have the micrographs. Firstly, we have the one labeled by the letter A, which is the untreated bagasse, in which we can't really see the fibers because they are hidden behind what in literature is reported as gum, made up mainly of lignin and hemicellulose. But in our case, we want to remove those two impurities, so we move on to the middle micrograph, which shows the sample after being alkali treated in the microwave. And now we can see the fibers, the cellulose fibers, but still there is some residuals on the surface of the fibers, as I mentioned earlier, confirmed by the infrared spectroscopy. And finally, in our bleach cellulose, which is the farthest right micrograph, which corresponds to our bleach cellulose, which has no presence of lignin nor hemicellulose, though it still has dimples caused by the roughness of our technique. And in conclusion, this approach produces, no me tardé mucho.